Okay, this is Matrices Day 3. So far, we've talked to you about a matrix, 2, 3, 4, 5, 6, 7, 8, 9. That would be a matrix. And tell me, what is it? A what by what? Don't say it, write it on your iPad. The one I just gave you there was a what by what. And does the rows versus the columns matter? Of course, it's huge. That is correct. Yep, yep, yep. Wait a minute, I'm afraid your first number might have been off, but I couldn't really read it. Yep, 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 yep. Nope, other way around. Yep, 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 yep. Okay, yep. It is 2 by 4 because the rows are 2 by 4 columns. 1, 2, 3, 4. 2 by 4. Okay. Now, if instead I asked you, what's this element right here called? I know it's 8, but it's usually, if this is matrix A, then we call it little a, and then there's something else. Do you remember what that element is called? You've got the right idea, but it's not called that. It's called A something something. Yours is close. It's missing something in between. Yours is exactly right. That's it. That's it. You need an A, and you don't need the R and the C. You don't need an X between them. There's something else in between them. That is correct. That is correct. That is correct. That is correct. Yes. 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 And most of you are doing this right with the little subscripts and a comma between them. You say how many rows and columns? It's row 2 and then column 3. So I made that too big. So 2, 2, comma 3. A sub 2, comma 3. That is your, hold on, there. That is your name of that little element. Okay, next thing is when we multiply matrices. Let's say I have 3, 4, 5, 6 as a matrix. And I am multiplying it by a matrix like this. 1, 2, 3. Can these two get along? Just because they're different, don't say no. How do you know for sure that they don't get along? Tell me. Yes. Okay. So what is this one? A what by what? A 2 by 2. And what's the other one? A 1 by 3. What's supposed to match up? These two are supposed to match up. Now, you'd think that just having the same number of numbers is what you need. It's not actually correct. You can have different numbers of numbers, but what you have to have is however many columns this one has, this one better have the same number of rows. Okay? So, if, for instance, I change this around to have 2 rows, it can have as many columns as I want. Okay, if it has 2 rows, like 5, 6, 7, 8, 9, 10, 11, 12. What's that? A what by what? The 2 by 4. As long as these match up, I'm good. Okay, if the number of columns here, like this, matches up with the number of rows here, then it's okay. All right, so then if these two match up, then the 2 and the 4 is what you're going to get out. We're going to have a 2 by 4 matrix as the answer. Well, I already know what that looks like, because that is a 2 by 4 right there. All right, so I'm not going to go through and do this whole one because it's the number is just too many numbers. I want to have a nice simple one. 1, 2, 3, 4, 5, 6, 7, 8. And if you multiply this, it is a simple one. It's a 2 by 2. And of course, if the other one's a 2 by 2, if these match up, then it's going to work. And this is what kind it's going to be, just what you'd expect. It's going to be a 2 by 2 answer. Would everybody please make me a 2 by 2, and if you know how to do this already, because you either watched the video last night or you were here yesterday when I taught you, write down what the answer is. If you don't know what's going on, wait a second, and I'll show you how to do it. Okay, how many of you are confident that you know those 4 numbers? Okay, there's only 2 people confident, 3 people maybe. All right, so here's how you do it. This spot right here, there's 4 of them where the answers are going to go. This spot here, would you agree it is in row 1 and column 1? So you take row, remember the order always matters. Okay, you have to do rows in this one and columns in this one. You never do it the other way around. The left side matrix is always going to use its rows. The right side matrix is always going to use its columns. And then you put these numbers together. The 1 and the 5 are corresponding. Like this is the first one of these 2, and this is the first one of those 2. So what do you do with the 1 and the 5? Well, the whole problem is it's a multiply problem. So 1 times 5. 1 times 5. Plus the other 2. The 2 and the 7 that correspond with each other here. And 2 times 7 is 14. So 1 times 5, which is 5, and 2 times 7, which is 14. 5 and 14 make a total of 19. So this element right here is 19. Raise your hand if you had that right, actually. And almost everybody did. You just weren't confident. Okay. So then, for those that are just learning this the first time, would you just try one more? Go to that spot, which is row 2 and column 2, and try to circle the right things and use them to get the answers. Okay, you should have said row 2, column 2. The 6 and the 3 correspond, 18. 8 and the 4, 32. 18 plus 32 goes right here. What is 18 plus 32? Let me think. 50. Raise your hand if you had 50 there. Okay, good. I think you get the idea on how to multiply matrices. Now, if you don't understand that well enough, go watch the video if you missed it yesterday. All right. Now we got to move on to the new stuff for today, which was, here's our first page of it. Okay. An identity. An identity is something like, you know what your identity is. It's what makes you you. One of the weirdest things for a person to have happen to them is for them to not remember who they are. And every now and then people get their head clonked or they go through some traumatic experience and they can't remember who they are. Okay, that would be a really weird thing, wouldn't it? You wake up and you don't know, like, how did you get here right now? You know, like, who are you? Where did you grow up? Who are your parents? What's your name? And anyway, identity for a number is just if it starts out as 7 and I want to keep its identity, there's a couple ways to do it. If I start with 7, what can I do to a 7 that will actually not change it at all? What about 1? Times it by 1. That's the multiplicative identity. Okay. What else could you do to a 7 that would keep its identity the same? Add 0. That's the additive identity. That makes sense? All right. So these are the things that keep it the same. So what can you do on a identity? You would think it would be 1, 1, 1, 1. You know, you multiply this by 1, 1, 1, 1, and it would stay the same. I want you to just try it for a second and get me the first couple answers in this identity. Remember, if this spot right here is row 1, column 1, you line up the row 1 and the column 1, and do you get pretty quickly that you are not going to get a 5 back? Here's row 1, here's column 1, and you get 5, and then you get negative 4 times 1 is negative 4, and 5 times negative 4, or no, 5 plus negative 4 is 1. The right answer for that spot right there is 1. That's not what I wanted. I wanted it to bring the 5 back. Can anybody smart enough to, without looking ahead, know what the right identity is? Some of you probably already have looked ahead, but all right, fine. That would be the identity. If you make it a 1 and a 0 here and here, then when I do the multiply problem, I get back the original that I had. Since I know that, I can just jump right to the answer. 5, negative 4, 1, and 8. I want to prove it to you. Let's say I just want to prove the 5 to you. Then row, column. Multiply them, 5 times 1. Get what's going on here. That's going to get times by 0 and it disappears, so it's just the 5. So 5 plus 0 is 5. That's how you show you how it works. All right, so in matrices, a 1, like multiplied by 1, is really like this. That's the identity matrix. It's true for any matrix. So let's say I had something a little bigger. Then you need a bigger identity matrix. All right. So this is like 1 in matrix form for multiplying. So if you want to multiply by 1, you multiply by this. Okay. Does the order matter? I think we talked about this the other day, maybe, that like if you do a 2 by 3 and you multiply that by a 3 by 5, just tell me ahead of time by looking at this, is it going to work? Yeah. What if I were to rearrange it and put the 3 by 5 matrix here and then put the 2 by 3 matrix there? Now is it going to work? That's a quick and easy way to show you that if you multiply matrix A times matrix B, and then you reverse it and do matrix B times matrix A, you do not get the same thing. Sometimes it doesn't even work. Now, if they're square matrices, they'll always be able to multiply by each other, but you'll get different answers. The answer for A times B is different than the answer for B times A. I think sometimes we assume in math that all math works the same under the same rules. Like, for instance, that, A plus B is always equal to B plus A. That's true for all the numbers you're used to, but it isn't true for all numbers everywhere. In multiply, you're used to that if, like, you go 5 times 3, it'd get the same thing as if you did 3 times 5. But that's true for the numbers you're used to, but it's not true for matrices. For matrices, if you reverse them around, you get different answers. Okay, so just let's get the first number for each of these. Find the first answer for both of them. I just want you to see that they're different. Oh, brother. Okay. 5 times 1 is 5, and negative 12 makes negative 7. Did I get that right? For my first answer of this matrix. Versus over here, 5 and 2. 5 times 1 is 5. 2 times 1 is 2. 2 and the 5 makes 7. It's close, actually. But it's not like it's just going to be like opposites of each other either. It just happens to be a 7 and a negative 7. It doesn't always do that. But definitely, bottom line, they are not the same. So does the order matter? Yes. Okay, moving on. On these special ones, will the order still matter? Let's test and see. Just get the first answer for each of them. All right, row 1, column 1. The 1 goes with the 1, the 5 goes with 0, and the negative 6 goes with 0, so it's just 1 times 1 is 1, plus a couple zeros is 1. The answer on the other side, row 1, column 1. Looks like it's going to be a 1 again. Just because I proved that the first answer is the same, does that mean that they're for sure all going to be the same? No. Let's try another more random spot. let's find the second element of each matrix, which let's call it this one, where I'm putting a star. Find me that middle top one. How do you do it? For those of you that are new at this, ask yourself where that little star is. Is it row 1, column 1? No. That little star is at row 1, but column 2. So you use row 1 and column 2. So in this case, it's a 5. Row 1, column 2. In this case, it's 5 again. Starting to get the feeling now? I guess it's probably going to work. Now, it's just one last spot. Row 3, column 3, the spot that's at the very end. Row 3, column 3. It's going to be an 8. Row 3, column 3. It's going to be an 8. Looks like it's the same, so the identity matrix can go both ways. It's really, really special. Okay. Moral of the story. Order matters on almost all the problems. Okay, there's always an exception. In this case, it's the identity matrix can go both ways. But only that one. Any other problem? B times A is not the same as A times B. Okay. What's a determinant? They're a lot like discriminants. They tell you the answer. No, they tell you about the answers, but they don't give you the answer. Let me give you an example. Do you remember x equals negative b plus or minus square root b squared minus 4ac all over 2a? Know what I'm talking about? Do you remember that this part right here could tell us whether or not this was going to fail? Because if it was negative, it would crash the thing. If it was 0, there'd only be one answer. So it kind of like told us about it, but it didn't actually give us the answer. So the same idea with this. A determinant tells us whether or not this matrix is going to play nice or not. All right? They tell you about the answer. So what is a determinant? You take your numbers and you do a special thing to them, and that's the determinant. So the determinant of a matrix for a 2 by 2 in general is defined by, so if you take this, it's AD minus BC. Did you get what they just did there? Here's A times D minus B times C. Okay? So, that would be like this times this, which would be what? Come on. Negative 8, and then what? Minus, and then 6 times 3 is negative 18. Notice I have to handle a minus a negative there, which is like plus. So negative 18, no, negative 8 plus 18 makes positive 10. That's your determinant. I'll tell you in a second what it means. It's kind of like, oh, you just did b squared minus 4ac and you found out it was positive, so it means this. All right, let's do this one. Should go quicker this time. What's that? 12 minus positive 12, and therefore it is 0. That's a different kind of determinant answer. So the determinant will tell us whether or not, no, I don't want to say it wrong. I'm going to wait till I get there on the slide. I haven't done this in a while. I don't want to say it wrong. Okay, what's an inverse? The additive inverse is like opposites. You take 3 and you add negative 3 and you get 0. Inverses are things that are like opposites. Where you add them, you get 0. A multiplicative inverse is like a reciprocal, and when you multiply the two things together, you get 1. So do you think what we're trying to lead up to here is there some kind of additive inverse for a matrix that you can add to it and make it equal 0? Yep. And is there some kind of special matrix that you can multiply by this thing and you will always come out to 1? Yep. So you've got to learn how to take inverses of matrices. All right, so what's this determinant thing do? All you need to know at this point is that if the determinant is 0, you can't do the inverse. So you remember we tested 2 of them, one of them came out to 0. If you do that determinant thing and you get a 0, then you can't have an inverse for that matrix. What does an inverse mean again? An inverse means you're going to multiply something like 7 times this thing times its inverse. And when you multiply it times its inverse, it'll equal 1. So in this case, 7 times 1 is 7. The inverse of a matrix. All right, so the inverse won't exist if the determinant comes out 0. All right, so here is 1 over the determinant. Do you get why we don't want the determinant to be 0? Because you'd have 1 over 0. You get how that would cause a problem. That's why you can tell just by looking at the determinant whether or not the thing's going to work. Because if you get a determinant of 0, you'll end up doing the problem and finding that, oh, it's 1 over 0. Wait a minute, I can't do 1 over 0. So you might as well just find the determinant first. And if it fails, it becomes 0. Then everything else you can just stop. It's kind of like doing a quadratic problem, where if you get a negative underneath the square root, you can just say, oh, it doesn't exist. So you start with the determinant part. And by knowing that answer, you'll know whether or not the whole rest of the inverse problem is going to work. Okay. How to find the inverse of a matrix. So let's see what they did here. This is the determinant thing. 1 over the determinant. The determinant on this one is 2 times 4 is 8 minus 2 times 2 is 4. 8 minus 4 is 4. That right there is the determinant. So then it's 1 over the determinant. And then what on earth did they do to that 4 and the 2 and the negative 2 and the negative 2? How did this turn into that? Anybody see the pattern? I'm going to call them A, B, C, and D. Can you tell how you get this to turn into that? You see it? What happens?
A and D switch places.
A and D switch places.
And then I'm not positive if C and E also switch places or just become A.
Good point. You can't really tell but they don't switch places. But B and C become the opposite of what they were. This became negative 2 and this became negative 2. So these two flip-flop and these guys change to the opposite sign. That's how you do an inverse. Now when you actually take this 1/4 and scale it by multiplying everything by 1/4, you get your final answer, and that is your inverse of the original matrix. Now, seems like that's a complicated process. It'd be nice if a calculator could do it, and it can. Everybody grab your graphing calculator. Okay. Okay, so we should, first of all, don't try to do this on your own. I'll show you how to do the inverse matrix thing in a second. But how could you solve this problem? What could you multiply both sides by? 1/3. Do you get that that's the inverse of 3? Now you'd multiply both sides by 1/3. Now in this world, multiplying by 1/3 on this side or multiplying by 1/3 on this side are the same thing. I mean, they both do the same thing, but remember in matrices, the order matters. So I'm going to put multiply by 1/3 in front on both, just to remind you that you can't just assume that you can multiply either way and have it come out the same. In matrices, you have to be more careful than that. Here, I could have multiplied by 1/3 on either side of the 15, and it would have been fine. And it comes out to x equals 1/3 of 15. 1/3 times 15 is 5, and therefore, there's my answer, and I used inverses. What's the inverse of 2/5? 5 over 2. And if I put it in front, I better put it in front. Only because when we do matrices, it's going to matter. This will cancel, x equals 5 times 10 is 50 divided by 2, which is 25, and there we go. You can use inverses to solve those, so you can use inverses to solve these. Do you get that if I got this off of here, I'd have x and y alone equaling something? So if I want to get 2, 2, and 2, 4 off of there, that matrix right there, I'm going to call it matrix A, then I would need to find its inverse and do its inverse on both sides, just like we just did with those fractions before. Do its inverse here and do its inverse in front of the 16 and 26. All right, we'll eventually show you how to solve that with inverses. So, first of all, let's just get into simple matrices on a calculator. Let's make this 3 by 3 matrix right here. So find the matrices button of the matrix menu. I'll pause for a second while I pull that up. Okay, got my calculator ready, and here's the matrix button. It is right above the x to the -1. It is, I'll hit second and then go right there and leave the key red so you can see where I went. Okay, once you're in the matrices menu, let's make matrix A. And so you'd think you just hit enter right now. You don't. If you did already, then go back, get back in here, quit out, and come back in. Because you have to edit matrix A. All right, and it says it's a 1 by 1. Well, I want it to be a 3 by 3. So that's the first thing you do is you say what it is. 3 by 3, enter. Now put a whole bunch of zeros in to just kind of hold the places. And now I can type it in. 1, enter. 5, notice it moves to the right, enter. -6, make sure you use the negative. If you use a minus key right there, it will fail. Your matrix will like crash and you won't know why. And the negative key, and then a 1, and then a 7, 12, 10, -5, and an 8. Okay, good. I got all my 3 by 3 matrix in there. Now, we're going to find the determinant by using the math option. Okay, so if we go into math and we want to do a determinant, I'm not sure it's under math. It says that on the screen, but I think it's somewhere else. Let's pause for a second while I find it. Okay, yeah, I had misunderstood what the board was saying. We have to be in the matrix menu, so we're still in the matrix menu. Then we go to math on the matrix menu, and then see DET. So determinant of, and which do we want to do the determinant of? Matrix A, B, C, D, E, F, or G, and it's just A. So now I got to go back to the matrix menu, matrix A, and now I've got determinant of A. It'd be nice to just have the symmetry of adding that last parentheses. Technically, I don't think you even have to. It'll figure it out without that. But enter. The determinant is 1146. Do you remember what that means? Do you remember it'll be fine as long as that's not what? 0. If the determinant had come out to 0, that'd be a big red flag that this matrix isn't going to play nice. I'll do that again. Everybody that had trouble doing that, get to a blank screen. Just quit out of everything you're in. Now I'm going to go to matrix. Let her do it. Let me show. Okay, so right now get in the matrix menu. Are you there? Okay, and now I go to math, and it says DET. Once you get that on the screen, now you got to go back to the matrix menu and find the matrix we want, which is our matrix A, that first one. Hit enter. Now it says determinant of A. And now I hit end parentheses and enter, and it's 1146. Okay, a lot easier than doing it by hand. What else could we do? Let's go back into the matrix menu. And under math, do you see identity? It's got the identity matrix in there. Yes. You don't want to type in A.
No, I don't.
Okay, so I'm in the matrix menu, and now what do you type? Oh, I hit it wrong.
And go to edit, and it shows up like how the
Okay, does it say matrix A right after, or does it say matrix C? It depends on which one you're in. Let me show you. If I'm back here, look at my screen for a second. If I was down here on C, when I went to edit, it would edit C. So you got to be at A and then go to edit matrix A. Okay, so back to, what else can we do with these? We want to know how to do inverses. Do you know what the calculator button for inverse is? You'd think it'd say like INV, but it doesn't. Remember how matrices were right above the x to the -1 button? That's not a coincidence. Because a lot of times in these problems, you want to find the inverse of a matrix. The inverse is the x to the -1. Okay, so everybody quit out, get to a blank screen, and let's even clear it so it really makes the point. You got a blank screen. Everybody get to a blank screen. You do it by second quitting, okay? I'm clearing it. You don't have to clear it, but for me, it's nice. All right, so now I'm going to go in and do, I want the inverse of matrix A. So the first thing I'm going to do is go to matrix A, enter, and there, I've got A on the screen. Now I want to do the inverse of it. The inverse is the x to the -1 button. There. See how A to the power of -1? That means inverse. If you take 2, for instance, and you put it to the power of -1, it makes it flip into 1/2. Know what I'm talking about? If you put in a 5 and then you said to the power of -1, it would make it 1/5. Okay, so power of -1 does inverse. I hit enter, and there it is. Now it's too big. It's all these nasty decimals for us to even see it all. But this is the same size matrix as before, except with the inverse in it. So that's how to find the inverse of a matrix. We aren't going to give you ones that have 16 decimal places for your problems that you'd see on the test, for instance. All right, so let's set that aside for a minute, and I just showed you how to find that. Remember, it was, you get the matrix on the screen, then you say to the power of what? -1. All right, so how could we solve this simple problem with matrices in them? All right, first thing, if this had been a normal equation, do you get we would want to do the opposite of this first, and then we divide everything by 2? With matrices, there's no such thing as dividing. But instead of dividing everything by 2, we could multiply everything by 1/2. Okay, so first thing, though, is we do the opposite of minus this matrix. So we add that matrix to both sides. Plus 2, 2, 2, 4 on both sides. Now adding Doesn't matter if it's A, B, or B, A. Like, you can reverse them and it'll add just fine. But I know that's going to cancel that, and yay, it's all gone. So 2A is equal to whatever I get when I add these. 6 plus the 2 makes 8. 10 plus the 2 makes 12. 14 plus the 2 makes 16. And 16 plus the 4 makes 20. That's pretty easy, wasn't it? Just add that one matrix to both sides. Next, how am I going to get rid of my 2? Multiply both sides by 1/2. Okay, so 1/2 of the 2, I put a 1/2 right here. And I multiply this times this, cancels. A is equal to 1/2 of all of these, so that'd be 4, 6, 8, and 10. There's my matrix. That was a matrix equation. Here first. Okay, it's been a long lesson. We're getting there though. So on this one, what are you going to start by doing? Just tell me. Add the matrix. So you'd add 1, 2, 3, 4 to both sides. And that's gone now. And then what are you going to do to both sides? Don't say divide by 3. Times by 1/3. So if I can do this problem, which you all can, and then I just times by 1/3 in front of both sides. I'll do a 1/3 times whatever that answer was to the matrix. Then I'll get my final answer. Easy peasy. Okay, so here's the harder kind. I'm not even going to assign any like this tonight, but I just want you to think. How could I get rid of this? Multiplied by, kind of not really the opposite. What's it called? The inverse. Multiply by the inverse. So if I found the inverse of this, and I did it on both sides, you can use the calculator to do it. It's be some decimals, 0.355, 0.75, or 0.9, or whatever it is. But if I do it to this side, I have to do it to that side. And you remember how the order matters? So you just got to be careful. If you do it on the left side or the right side, you better be consistent. And I'll tell you more about that later. Okay, that's just big picture. That's generally how you do it. All right. Whew, we have learned a lot of stuff. Determinant. Determinant was that thing where you go, let's say it's 3, 4, 5, 6. Determinant was this times this and that times that, and then you subtract them. What's the one thing you want to watch out for? If it turns into 0. If it doesn't turn into 0, everything's good. Inverses. You're going to use the calculator to find the inverse. I showed you this complicated formula for it, but we won't make you do that by hand. The inverse on a calculator is the x to the -1 button. Okay. The identity matrix. If it's a 2 by 2 matrix, do you remember what it was? 1, 0, 0, 1. That's the identity matrix for a 2 by 2, and of course it's very similar. Just has ones running diagonally like this on bigger matrices. All right. Let's see. No need to memorize formulas. You're not going to use calculators today on your homework because we're making them easy enough that you can do them by hand. And what does an identity matrix do? It keeps the thing's identity. So when you multiply by it, it stays the same. What does an inverse matrix do? It makes it like flip for a matrice. So instead of like 2/5 turning into 5/2, for a matrix, it does that same thing. And it's just this button on the calculator. And then when will an inverse not exist? If the determinant is equal to 0, the matrix will not have an inverse. All right, we've made it through. Now let's do some homework together. Everybody find the homework. It's easy days and hard days in here. The last 2 days have been pretty easy. This one's a harder one. It's not impossible, but there's your homework. I'm going to download it so I can write on it easier. And I will cut some of the problems off because I don't have too much time to work on this. So, I'm just going to get an overview of how many there are and stuff. All right. The beginning here, these aren't as important, so why don't we skip this one and this one And this one, 3, 6, and 8. I ought to cut it down a bit. All right, state the determinant. Oh, determinants are so easy. That's just this times this and that times that. So what's 6 times 6? Or negative 6 times negative 6? 36 minus, what's 6 times 0? 36 minus 0 is? 6. Is that going to be a problem matrix? That's all you're really finding. No. If it had equaled 0, it would be that problem matrix. Okay, that times that, negative 4. That times that, minus negative 1. And negative 4 minus negative 1 makes negative 4 plus 1, which makes negative 3. Is it going to be a problem matrix? Nope. As long as it come out to 0, it's good. It can be negative. It's no big deal. All right, and that last one would have come out to 0. All right, next up is state whether or not the inverse of the matrix exists. It's the same thing as before, except you got to know that if the answer comes out to 0, the thing's matrix, or the thing's identity, inverse, the thing's inverse doesn't exist. All right, so one of these is going to come out to 0, or maybe more. And if they come out to 0, thing doesn't have an inverse. All right, finding the inverse of each matrix, no calculator. Oh my gosh, we didn't do that last year. Okay, well, I guess I don't want you guys to be weaker than the other kids who are going to have to learn how to do this without a calculator. So you can use that formula. It's the 1 over the determinant. And then do you remember how these two flip and these become the opposite of each other? Make that little drawing I just did with the arrows like showing switching and the negatives showing become the opposite. And I'll show you how to do number 7 here. So you go, first of all, what's the determinant? Negative 11, negative 10, negative 11 plus negative 10 makes negative 21. Sure I did that right. The determinant is minus, sorry, minus negative 10, which means like plus 10. Negative 11 plus 10 is negative 1. There we go. Okay, so the determinant's negative 1. So I go 1 over the determinant, negative 1, which is the same as negative 1, times this thing. I got to flip-flop the 1 and the 11. These guys get flip-flopped. Negative 1 goes here, 11 goes there. And then the other two become the opposite of what they were. The negative 5 becomes 5, and the 2 becomes negative 2. Now how do I do this? You just take all these numbers, multiply them all by negative 1. Because negative 1 over 1, or 1 over negative 1 is negative 1. So negative 1, and you times it by all 4 numbers, and you'll get your final answer. That's how you do inverses without the calc. Thankfully, the assignment's pretty short. I am revoking, I'm sorry. I'm going to have you skip, you can't skip number 8, because I did number 7 for you, so you need to do number 8. And last, hold on, I gotta erase this stuff. It's about finding that product. I will let you skip on the calculator allowed side. Skip number 13. Just do number 12 there. And you can skip number 18 also. That'll make this a reasonable size for tonight. 13, 18, 3, and 6. 3, 6, 13, and 18 are skips. Okay. I know this was not a easy peasy day, but the last 2 days were pretty easy. So, and you're in an honors class, you got to be able to step up now and then. It's one of those days. Okay, that's all I have for you for today.